Hello and welcome back. And today is going to be the last day of streaming for this course. Tomorrow, of course, is the official last day of the class. But today we're just going to do a review. And the form that that's going to take is we've got our final exam here from a couple of years ago. Or I guess it was from last year. We'll go ahead and do that along with some other questions here that I've got prepared in order to help you review for your final exam, which will be released tomorrow, midnight tonight, basically. And then you'll have until midnight tomorrow to complete it, upload it to Canvas just like you did your midterm. So remember, we are on Piazza. I am available on YouTube here. If you have any questions, go ahead and shout them out. Otherwise, let's go ahead and start with this first problem here. Let A be a set of integers, and let K be another integer. The subset sum problem is, given A and K, does there exist a subset of A such that the sum of elements in S sums to K? So let's go ahead and design a brute force algorithm to solve this problem. We're going to give good pseudocode and a full analysis of it first. Okay? So let's go ahead over to our tablet here. That will be saved for later there. So I want to design a brute force algorithm to do this. First of all, let's understand what we're talking about. So we're given a set of integers here, 8, 4, 7, 3, 2, and 5, right? And our integer k here is, I don't know, 14, right? So does there exist a subset of A such that if I sum all of the elements in S, right, then that's equal to K, right? In fact, I'll use a different symbol for the elements in S. I'll just call it X, right? So, for example, if I started out with a subset like 8, 7, 2, and 5, right? Then the sum of that is going to be 22, right? And that's not equal to K, so that didn't work. If I start with a different set, say, this is the one I was thinking when I made it. There we go. That does sum to 14. So yes, we would answer yes and output. Yes, there does exist a subset of size not size k, but whose elements sum to k. Okay. So here's our brute force algorithm. Our input again is going to be a set of integers. Doesn't necessarily need to be unique or non-unique or something like that. A1 through an, and an integer k. And our output will be true if there exists a subset S of A such that the sum of all elements in S is equal to K. Right? So I'm just going to use the power of pseudocode here. For each subset S of A, I'm going to just sum them up, right? In fact, I'm going to use the symbol above here. You don't have to write a for loop for each element X. I guess we could. We could go ahead and say for X in S, right? Well, I'll have a total here that I'll initialize to 0. But then I can go total plus equals X, excuse me. Right? And if the total equals K, output true. But again, the power of pseudocode here, you know how to sum numbers, right? You know how to write a for loop. All we need to do is have a one-liner here. So sum, I guess I called it total. I'll go ahead and keep that. Is going to be the summation of all X in S. Right? That's pretty clear. You're using mathematical notation here. Otherwise, we'll output false if we go through all possible subsets and then never find another one. Now, you could design, as an alternative to this, you could design a backtracking solution where if you start adding an element, add an element, add an element, and if you ever exceed the sum of k, then you backtrack. Don't bother adding anything more. The larger subsets are just going to contribute more to your sum, and you've already exceeded k, so backtrack and redo this, right? But as I've now, in the worst case, of course, it's going to be the same, where you have to actually look at all possible subsets. There is, you know, you can be a little bit clever about it and sum up all the elements and see if that even exceeds k or not, and then immediately stop and answer no. But otherwise, there aren't many tricks in general that you can do to cut that down from exponential. This is going to be order 2 to the n because you're generating all possible subsets. This is, you could say that this is order n, right? Because it's actually going to be order the size of the subset, right? Which is bounded by order n. But that's not really all that important. I mean, that would only add an n out front here, right? All we're expecting here is that it's going to be 2 to the n, because how many possible subsets are there of a set of size n? 2 to the n. Okay. What's our elementary operation? Maybe computing the sum, right? And then we come up with this. So I don't want to focus on that too much. Instead, let's go ahead and look at the second part of this problem. It is well known that this problem is NP complete. You don't need to provide a full proof of this, but we do want to show that it is in NP by giving a non-deterministic polynomial time algorithm for it. So remember, a non-deterministic algorithm is going to have these two phases where you guess a solution and then you verify. So our input here is going to be the same. In fact, I'm just going to steal it. All right. Our input is a set of integers. Our output will, now we're going to change the output here. We'll accept if there exists a subset of S whose values sum to k, reject otherwise. So my first phase here is a guess phase. A subset S of A, right? And again, I'm just going to jump immediately here. This can be done in order n time. Again, it's going to be order k, or order the cardinality of S, but that's going to be bounded by n. Right? 2, verify. Right? And all I'm going to do here is the same exact pseudocode that I did before. The sum will end up being the sum of all x in S. And if sum is equal to k, accept. Otherwise, reject. And you're done, right? This is, of course, going to be order n. But the thing is, this is deterministic. This is non-deterministic. So you can say that this is a linear algorithm, but it's non-deterministic linear, right? So this is enough to show that this subset sum problem is in NP. Okay. If you wanted to show that it was NP complete, you'd have to show a full reduction from a known NP complete problem, like Hamiltonian path or something like that, in order to complete the proof. But that's not what the final here is asking for. The third part here is that Gomer has come up with a dynamic programming solution that does correctly solve the problem. So Gomer has a lot of problems here, but one problem, but correctness is not his problem, at least in this instance. For this problem that fills out a tableau of size n by k, and so it has a running time of order nk. He's also correct about that. He rushes to publish his results showing the claim that P is equal to NP because this is clearly polynomial, right? Briefly explain why Gomer is wrong. Again, this is the same problem as the knapsack problem. In fact, you would show that the sum problem here is NP complete by an easy reduction from the knapsack problem. It's just a knapsack problem in disguise. Instead of optimizing your values, you are asking, is there a knapsack, a subset that is exactly this value? And he's wrong because we already, for both of those problems, it's pseudo-linear, right? That k is not necessarily bounded by a constant all the time. That k could be exponential in n. Because their input size is n, right? Then you're allowed to, for the input size of k, it's log n, or whatever k, or sorry, it's log k, whatever k happens to be. That could be as big as n. And so when you expand that out, you get that it could be as big as 2 to the value could be as big as 2 to the n, meaning that entire table that you fill out could be exponentially sized. That's why he's wrong. It's just the same question that we went over when we went over the 0-1 knapsack problem. Okay. Design an algorithm. Let me go ahead and zoom in here. There we go. So design an algorithm that, given an undirected graph G, counts and outputs the number of connected components G has. Recall that a connected component is a set of vertices that are all connected by some path. Give full pseudocode for your algorithm and a full analysis. Name your algorithm num components. Okay. So we're going to go ahead and design this algorithm here, but we're not going to design it from scratch. Just like usually, you can reuse code in a library or reuse code that you've used in an assignment before. You can go ahead and reuse pseudocode that you've designed before or that I presented before. So remember that, recall that we have this DFS subroutine that takes a graph G and a starting vertex S and explores S, coloring vertices black once completed. And remember that we potentially had to restart our DFS. We had to restart it if it was a disconnected graph, because you would explore this. This region over here of connected vertices, but there is this region over here with other vertices, and maybe this region over here with these vertices, right? And it was a disconnected graph. And so if you did a DFS or a BFS or whatever starting over here, you would end up coloring in all these vertices, and that's done. But then you would have to restart it. Look at any unvisited vertex, start that again, right? And complete the DFS starting from that vertex. And you would call this DFS every single time until they were all, completed and colored black, right? So we're going to exploit that fact here, right? We're going to suppose that we have access to that function, that method, that algorithm, that pseudocode, okay? And we're going to use it as a subroutine here. So here is our num components of a graph G. My input is going to be a graph, not necessarily connected, because of course we're trying to determine if it's connected or not. G equals V comma E. Right. And our output will be not the DFS, but a number. The number of connected components of G. Okay? All we need to do is basically cut and paste from that that main DFS routine. And initially what it did is it colored all the vertices white. So color, or let's go ahead and go with for each. X in the vertex set, color X white, and this is unvisited. Again, we go with white, gray, and black simply because it's easy to visualize. If you were to actually code this, I wouldn't call them white, gray, and black. I would call them what they are: visited, unvisited, processed, complete, whatever. Right? Hopefully you did that when you did your assignment. And then I'm going to, I'll go again for each vertex X in V, right? If I'm going to let me give myself some more room here. I'm going to move this down. There we go. And I'll come back up there in a second. If X is white, then I will go ahead and perform that DFS subroutine. Oops. A little bit more judicious. On G, starting at X, right? And then I'll increment a counter. I could do it before I did it, I guess. Count plus plus. Right? And there's my for each. And so I'll initialize my counter to 0. Okay? So what am I doing here? This counter is counting the number of connected components. Initially, if there's one connected component, of course, it's going to be incremented here. And then this one subroutine call here is going to end up coloring them all black. Right? And they've all been processed. Meaning that when I come back up to my for each loop here, I'm going to break out of that because there are no, I'm not going to break out of it specifically. Okay. I'm glad I said that because I just discovered a bug here, right? So I don't actually do it in this loop here. Where do I do it? I do it here. Every time I actually have to perform a DFS. Because otherwise I'll go over this loop here. Extend this down. And I'll discover, okay, well, there's a black vertex, and so it's already been processed, but if I increment my counter, of course, I'm going to end up with just n, right? A trivial answer there. Only when I need to perform a DFS do I increment my counter. After this for loop here, I'll just output the count. And if I were actually coding this, I wouldn't call it count. I would call it num components, right? Number of components or something like that. And again, this DFS subroutine, we did that in class. You can, of course, assume that you have this. There's no need to cut and paste it. Just like there's no need to rewrite your sorting algorithm in Python or C. There's no reason to write your own square root algorithm in those languages. They're built in, right? This is built in, at least as far as this course is concerned. All right, so we output this and we're done. So that's num components. Okay, let me go ahead and go back over here. Give full pseudocode and a full analysis. Okay, fine. Let's go back. So what's the analysis here? Well, this is going to be order n here, the initialization, but that's not going to be all that important. It's going to end up being dependent on this DFS here. And of course, we might have to restart it. So we're not running DFS n times for every vertex. If it ends up coloring them all black on the first one and there's only one connected component, then we've ended up only calling DFS once. So the complexity here is the same as DFS. Right? And for that, you can go back to your notes and say that it's order n plus m, right? That's the number of vertices plus the number of edges, and then you can, of course, bound that by saying that it's order m, because m is, if it's a disconnected graph, m could be less than n, but either way, right, you're going to have you can leave it like this. Right? Okay. Let's go back. No questions so far. Number 3, design an algorithm that, given an undirected graph, determines if G is a connected graph. That is, all vertices are connected by some path in a disconnected graph, meaning that there is more than one connected component, right? Give full pseudocode of your algorithm in a full analysis. Name your algorithm is connected. Right? So not only could we use DFS as a subroutine in our last answer, but guess what? We're going to use the num components that we just wrote in this answer. Right? So the input, in fact, I don't like rewriting, so I will go ahead and cut and paste this. And modify, because it's no longer num components, but it is, what was it called? Is connected. Right? Our input is the same, but instead of this output being the number of connected components, it's a decision problem. The output is going to be a true or false statement. So it's going to be true if G is connected. Who would have thunk that, given the name? False if disconnected. So hopefully you see the solution here immediately. Num, or actually I'll just call it K. I'm going to call my num components algorithm that I just wrote. And if K is equal to 1, output true, because there's only one connected component. Otherwise, output false. There's more than one connected component. Right? So what's the analysis here? Well, our elementary operation is calling this function, and calling this algorithm, calling this pseudocode, calling the function, method, whatever you want to, however you want to view it, and it's going to be the same. Right? You can see how this this exam was designed, right? So that you could reuse this stuff. That goes again back to the idea of reductions. All of these are basically the same problem. They reduce to each other because I can use a solution for one of them to another one of these problems. Right? 4, let G be an undirected connected graph. If E is an edge cut, an edge cut, an edge is an edge cut. If you had removed it, then it becomes disconnected. Design an algorithm that, given an undirected graph, determines if G has a cut edge or not. Give full pseudocode for your algorithm and a full analysis. Okay, so let's come back over here and understand what we're talking about here. Right? So here's a graph. Right? Now, if I were to remove any one of these edges, it would not result in 2 disconnected components. If I were to remove another one there, if I were to remove 2, then certainly I could cut this and disconnect this graph. But that's not what we're asking. That would be an edge cut set, and you can talk about that. But another graph, say a bow tie graph, kind of like this, there is an edge, a cut edge, right? The cut edge is right here. If I were to delete that, then of course I would have 2 connected components here, and I would end up disconnecting the graph. It was connected before, but now it's no longer connected. Okay. So how do we design an algorithm to determine, is there an edge cut? So my input is going to be a graph G equals V comma E, right? And we could also put a restriction here that it's going to be a connected graph, because if it's already disconnected, maybe you'd have to come up with a little bit stronger or a rigorous definition. But you could say that it's still a cut edge if it results in at least one more connected component or something like that. There's your spoiler for how we're going to do this. Output true if G has a cut edge. Right? In fact, we could also output a cut edge if there is one. There might be more than one if we want to. Otherwise, I'm just going to go true here or false because that's what all that's all the only thing that it asks for. False, otherwise. Well, guess what? For each edge in the edge set, all I'm going to do is create a new graph, G prime, which is going to be the same vertex set, but the same edge set, but without E. So set minus E. And then I'm going to go all the way back over here and ask, how many components are there? Right? Or actually, no, I'm not even going to do that. I'm just going to call is connected. So num components is connected called that. This is going to call connected. So if not is connected on G prime, then I will output true. Remember, we took the edge out of this graph right here, and then we asked whether or not it was connected. If it's not connected, then that was a cut edge, and we output true. Otherwise, now we can't just go else there. What we have to do is we have to go through all the edges. Is this a cut edge? Is that a cut edge? Is the third one a cut edge? And if none of them are cut edges, then we output false. Okay. So again, what's the complexity of this? Well, you do have to be careful here, right? Because this is order M. Right? And it calls is connected as a subroutine, which we've already said is order M plus N. So if you do it like this, this is going to be order M plus N. And so all in all, it's going to end up being order M times M plus N, or order M squared. At that point, you can really get rid of the N, because M squared is M is already N squared, and so if you square that again, you could say that this is bounded by order N to the fourth, right? But we'll just go ahead and leave it like that. Still no questions. All right. So this last series of questions is simply just given this graph here. Perform a depth first search on the graph. Use lexicographic order to determine which vertex is next. Indicate the discovery order and finish order of each vertex. Perform a breadth first search on the graph in Figure 1. Use lexicographic order to determine which vertex to visit next. Indicate the discovery order, finishing order. Then finally do a minimum spanning tree. Indicate which algorithm you're going to use and the order in which the edges were considered, which edges are included, excluded, and the total weight of the resulting minimum spanning tree. So if I see we've got like 7 people online. If I see a yes, do it in the next 10 seconds here or so, then we'll go ahead and come back to this and do this. Otherwise, you wrote these algorithms. All you'd have, one very easy way of doing this would be to take this graph, put it into the text format that you used for assignment 3. Okay, I see a yes there. Put it into the text document for assignment 3, and then run your code. Right now, you would have to, of course, change the breadth first search criteria, because I think that one was order of weight next. But you could very easily do this by outputting more from assignment 3. Right. So I did see a yes. So let's go ahead and do it. Right. There we go. want it that big though. All right, so let's do a DFS first. And it did say to start at A. So that's where we'll start. Okay. My highlighter here. I'll go ahead and color it gray. And I will also mark the discovery time as 1. We haven't finished with it yet. But I will go ahead and also mark the tree edges if you wanted to draw the entire DFS tree. We're going to go to B next. Why do we go to B? Well, we've got this neighborhood here, and it's connected to B and F. But if we're going to go in lexicographic order, B comes before F. Okay? That has now been discovered at timestamp 2. So discovery time times A, then B. Then I'm going to look at its neighborhood here, and I see A, but it is colored gray, so that's where I came from. I'm obviously not going to backtrack there. I see E, D, and C. That which is lexicographically least is going to be C, and that's discovered at timestamp 3. Right. So C. I'm now at C. I see a neighborhood of B, D, and H. B is, of course, gray, so I would not go to it. I see D and H, though, and the lexicographically next one is D. And that's discovered at timestamp 4. And we'll go ahead and highlight that gray. All right. Now I'm at this, node here, this vertex. I see a neighborhood of B, C, and G. Well, of course, those two are gray, so I'm not going to backtrack there. So I will go to G next with a timestamp of 5. Note that I have not backtracked yet at all. I've not completed any of these nodes. Color it gray and mark the path that I followed. There we go. And note that it was G next. Okay. All right. And then, of course, we'll have processing order. Which I haven't gotten to yet because I have not processed anything. I'm at G. Its neighborhood is D, H, E, and F. But again, this is gray, so I'm not going to go to that. Among E, H, and F, E is the lexicographically least next. So mark that at timestamp 6. And E, go to the next line here. At that point, I'm looking at a neighborhood here of F and B and G, but B and G are both gray, so I don't backtrack. Instead, I go on to F. Discovered at timestamp 7 and colored gray. There we go. I look at its neighborhood and I only see gray vertices here. So I start to backtrack, right? That I complete F and process it, F. And I will color it black. For me, that's just going to be another shade here of the highlighter. There we go. All right. Backtrack, where did I come from? I came from E. And its neighborhood has been completely destroyed, but explored. Right. Came in and wrecked everything up. Right. So E is next. Right. We backtrack to now G. Right. But if I look at its neighborhood, now I've got a whole variety. I've got 2 processed black vertices. I've got 1 visited but unprocessed vertex D. But I've got an unvisited vertex here, H. And so I continue to explore that depth. Right? And I discover H at timestamp, where are we, 10? I think I forgot to put down F here. So I'll do that now, and then H. And at that point, I'm done with my discovery times here. And you can pretty much write them all down, but I'll go ahead and go through the full gamut here. H's neighborhood has now been completely explored. So again, we start backtracking here, and H has now been completed, and we highlight it black. There, done. We backtrack to G, and its neighborhood has been completely destroyed. I keep making that same mistake. Let's just go with it. All right, it's been destroyed. Right, and then I backtrack to D because that's where I came from, and its timestamp there is 13. Backtrack to C, B, and then A. So processed, 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 C, B, A. There we go. This is not the reverse of this. If you were able to somehow explore the entire graph all in one shot, one big line, then sure. But otherwise, if you have to backtrack and then go down another corridor, then it's not going to be the same thing as this up here. But otherwise, we've got our discovery times, we've got our processing times, and that's all we needed to show there. So same exact thing, but for BFS. And again, we'll start at A. So BFS, oops, BFS. And here I'm only going to do the discovery order. Did we even ask for the finish time? Oh, and finish order. It's going to be exactly the same because we're using a queue. So I guess we did ask that, but that's only because I was lazy and I cut and pasted. Maybe I was also trying to trick you. I just give the same exact answer and you're good. Right? So we'll go ahead and go with A here, discovery time 1. And we enqueue it. And I'll go ahead and visualize the queue down here as well. Enqueue it. It's not yet processed. When we dequeue it, that's when we process it. And that's why it's kind of useless to write down the timestamps here, because it's going to be the exact same order. It's not going to be 1, 2, 3, 4, 5, 6, but it will end up being the same order if you were to sort those. Okay. So A is out. I look at its neighborhood, which is B and F, and going in lexicographic order, B and F will be enqueued. They will end up with gray, and I'll go ahead and highlight the BFS forest here, the tree edges in the BFS forest as we're going along as well. I dequeue B, and I look at its neighborhood. You can process it before or after you've enqueued its neighbors. I'll go ahead and process it now. And I should have noted that B and F were next. There we go. And I'll go ahead and enqueue its entire neighborhood here, which in order would be C, D, E. C, D, E. And C, D, E. There we go. We're done with B at that point. I should have colored them gray though. And noted the BFS tree edges. There we go. Next, I process F. I see its neighborhood has a black vertex. I'm not going to backtrack. A gray vertex. I'm not going to enqueue that more than once. And I see a G here as my next vertex. G. So discovery of G for next. And it's colored gray. I'm done processing F here. There we go. And it's out of the queue at that point. Okay. Let's see, what's next? C. I look at its neighborhood, black, I ignore that, gray, ignore that, white. Let's go ahead and color that, and note that that was the last one that we needed. And the tree edges here. How did we get to G? We got there through D. How did we get to H? We got there through C. And then you would just end up DQ, 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 DQ all the way down. Right? Coloring these in the order that you visited them. So C, D, E, G, and finally H. Right? So there's enough to reconstitute the BFS tree as well. Right? The last question was a minimum spanning tree algorithm. I'll go ahead and do, let's see, Kruskal's or Prims. Kruskal's is really easy, right? All you would do is go in order. We'll take that edge. Here's really quick Kruskal's because you can do this so easily, so visually. 2, that's still not connected. So F and G and D are now connected. This is connected, but there's still disconnected components. The next one that I would consider is a 3. There we go. Next one would be 4. There's E. Next one would be 5. There's no 5s. 6 goes to B. No other 6s. So 7, 8, none. 9. And I would probably go from B here to break ties. And at that point, you're done. There's no other edges to consider because Kruskal's would be done at that point because you've connected everything. Okay? So that was a really, really quick version of Kruskal's. Let's do Prims. Remember, Prim, we don't have disconnected components. We start at a vertex. We'll start at A. And then you always expand out greedily by choosing the next fringe edge, or an edge connecting the tree to a fringe vertex, and you're always greedy about it. So let's go ahead and start at A here, and I'll highlight them instead. A, there we go. And I'm looking out at these fringe vertices, right? F and B. And both of them are 9 here. Right, so I would end up going with, arbitrarily, it's going to end up being, unfortunately, the same exact tree here, just by coincidence. And I've expanded my tree now out to these. Right? Now I'm looking at fringe vertices here, 9, or fringe edges, 9, 6, 12, and 11. And so I would end up choosing, of course, the minimum, being greedy about it. And I would end up with this. There. And I don't know I don't know what the sum of these was. You can do that math yourself. Right. But I am looking at the fringe vertices here. Again, 9 is still in my fringe. 4, 3, 12, and 11. And so I end up choosing the least one and incorporating that into my tree. Now my fringe is a little bit different. 2, 13, 12, and 11. And so I will again choose G. My fringe here is 3, 2, 12, and 11. So being greedy and choosing the minimum, I would then choose, I would then choose D. There we go. Now my fringe is 3, 10, and 11. Not 1 yet. So I'm going to select the minimum, which is 3. There we go. And now my fringe is 1, 10, and 11. Select the minimum, and it'll be this one. I didn't write those down in the order, but of course you can go ahead and replay the video and write them down yourself. Right? Okay. The last questions I wanted to go over were, I think that this is actually from 2019. Very similar questions. We just had a different graph, but I pulled these out because this might also serve as a good review for your final assignment, which again is due tomorrow at midnight. So suppose that we need to generate all possible combinations of vertices in a graph with n vertices for a brute force algorithm that we're developing. To do so, what order would the algorithm be? This is kind of what was in your midterm, just asked in a different way. Of course, you are all possible combinations of vertices. That's the key word there, combinations. It's going to be... we already did that. That was the first question. It's going to be subsets, so it's going to be order 2 to the n. Right? Suppose we need to generate all possible orderings of edges from a graph with m edges for a brute force algorithm we're developing. To do so, what order would the algorithm be? For ordered, right, the key word there is ordering. For ordered combinations, then we're talking about permutations. And if you're ordering m of them, then of course that's order m factorial, right? So 2 to the n and m factorial. Again, for more visual, it's going to be order 2 to the n and order m factorial. Okay. Now, suppose that P1 and P2 are in NP, the class of algorithms decidable by a non-deterministic polynomial time algorithm, a Turing machine, and that P2 is NP complete. Further, suppose that P1 reduces to P2. Can you conclude that P1 is NP complete or not? Provide a brief justification. So for this, I'm going to go ahead and draw our complexity landscape here. All right. So here's NP. Here's P. Right. Remember that it is contained in NP, and here is the world of NP complete problems. By the way, an interesting question would be, under one assumption, if P is equal to NP, well then of course all of these collapse and we don't have this 1, 2, 3 region. They're all the same. But if P is not equal to NP, then clearly this region and this region, they're not equal. But what about this region? And are there things that are not in P that cannot be solved in polynomial time, but that yet are not NP complete? Right? There's something indeterminate. This is called NPI. And the fact is, if NP is not equal to P, then that there is a language in here. And I forget who gets credit for that. Darn it, I can't think of his name right now. But you can, basically it's a diagonalization argument. You can diagonalize away, under the assumption that P is not equal to NP, then you can diagonalize away and say every other string or whatever will be in the same string as an NP complete problem, but every other string will be in P or something like that. It goes beyond this course here. So I'm not going to go back to the exam here, but instead I'll go ahead and visualize what the exam said. So P1 and P2 are problems, and they're in this world here. Okay, they're somewhere in here. All we know, though, is P2 is NP complete. It's in this section up here. Now, we do know that P1, polynomial time, reduces to P2. Right? Can we conclude that P1 is in NP? Well, first of all, it is in NP, but is it NP complete, or is it in P, or is it over here? Just given this reduction right here. The answer is we don't know, right? There's not enough information here. First of all, by saying that P2 is NP complete and that P1 is in NP, you've already trivially said this third part here. Because the definition of NP is that everything in NP, the definition of NP complete is that everything in this set, polynomial time, reduces to it. So we didn't even need this third statement here. We don't know where it is. It could be in P. It could be NP complete. It could be over here in the indeterminate area. Right? So there's not enough information to decide, and that's the justification. Right? D, suppose that P1 and P2 are in NP and that P2 is NP complete. So that is the exact same scenario there. Further, suppose that P2 reduces to P1. So it's just the exact opposite here. Can you conclude, though, that P is equal to NP? Right, so let's go back over here and redraw our complexity landscape. NP, NP, complete. And we've got P2 here. And here's P. We only know that P1 is in NP. The second thing that we know is P2 reduces to it. So, by implication, since a known NP complete problem reduces to P1, excuse me, then that implies that P1 is NP complete. That's all we know from those premises. Can we conclude that P is equal to NP? No. We still don't know anything about P1. We still don't know enough about P1 to make any conclusions. If we had that, if P1 were in P, then yes, that implies that P is equal to NP, because you would have this the other scenario there. Let me draw it in red. The other scenario that I just proposed here, that P1 is in P instead, and P2 reduces to it, right? That means that this entire thing collapses down to P. Because all you need is one problem to do that. Every problem reduces to this NP complete problem. If this NP complete problem reduces down to P, that collapses down to a problem in P, that collapses everything. If you could solve SAT by simply making a transformation to a graph and solving minimum spanning tree or something like that, then you would end up collapsing P and NP. Very, very unlikely, and it's certainly not that simple, right? There are a whole bunch of other barriers that you would have to get beyond, that go beyond this course. If you're interested in that kind of stuff, though, of course, you could take a course on computational complexity. Okay. Sorry, we had a question here. For DFS, BFS, MST, is that about how much work you would on a final for full credit? Well, I would expect, since you have 24 hours, that you would show a little bit more detail. For example, if all we're asking, this is probably enough. All we asked for was the discovery order, right? We didn't ask you to actually visualize the BFS tree, or with respect to DFS to timestamp stuff. Of course, if we ask you to timestamp stuff, then certainly you would need to show this kind of work. For prims, if we asked you to consider, like I said, I just did this visually. We asked you to consider to write out what edges you considered and in what order, and you said that you took this edge or you rejected that edge. If it were Kruskal's or something, we would expect that probably if we asked that, right? Okay, any other questions? We are in a 10-second delay here, so I'll go ahead and wait. Okay. Well, again, thank you for attending this summer course. It's always challenging to do a summer course because it's, first of all, it's a challenging course to begin with, Computer Science 3. But taking a 15-week course, compressing it down into 5 weeks, and then doing it completely online, good on you for making it to the end. Make sure that you get assignment 4 done, and that if you're going for all that bonus, go for it. I will be holding regular office hours today. On Thursday, we're not streaming. Remember that I am going to be holding extended office hours during the regular streaming time. So from 11 o'clock to 12:15 or thereabouts, you'll find me here. I'll probably be here, but eating lunch all the way till 1 o'clock, where my official office hours begin again. Sarah, of course, is here today and tomorrow, after which we no longer have daily office hours. We hope to get assignment 4 and midterm graded by over the weekend and done early next week, with final grades posting immediately thereafter. Make sure that you're checking the grade book. Everything is, all the data entry is in there and correct. But otherwise, again, thank you for attending. Thank you to Sarah for all the work that she's done. Send her your thanks as well. And good luck with your fall classes if you're continuing in the program, or continuing in your own program, or whatever you're doing. It should be interesting this year, but you know, hopefully everything. Stay healthy. Wash your hands. Get the vaccine. Wear your mask. Just, make sure that you're taking care of yourselves. Okay. All right. Have an excellent rest of your day and what remains of your summer.